Okay, students, let's get into section 4.4. Okay, let's talk about spanning sets. Okay, definition. If every vector in a vector space V can be written as a linear combination okay, of V1, V2, ... Can do V3 here. Okay. Okay, and these are all vectors. Okay. If I have the V1, V2, V3, if I have a V sub, that's generally going to mean vector, and so I'll sometimes drop the vector above it. Okay. Now, if it doesn't have a subscript, then it more than likely is a vector space. But or if I need to denote it as a vector, I'll denote it, with the vector above. But for this definition, I'll leave the vectors, the vector symbols above the variables here, the notation. Okay, this goes to V sub k. Okay, and comma, we say that V, capital V, these are lowercase v's. I know it's hard to just, make a discrepancy between lowercase and uppercase in handwritten English, but we'll try. Okay, we say that V, the vector space, is spanned or generated by all these vectors. By V1, V2, ... VK. Okay, and call this set of vectors V1, V2, ... VK. We call this set of vectors a spanning set for V. That is, okay, we can write vector V, okay, as a linear combination. There's that linear combination of vectors, C1 vector 1 plus C2 vector 2 plus ... plus C K vector K. So we can write this as a summation of these vectors and any constants, And, you know, if there exists C1, C2, all the way to CK, where this works, then we can say that we could write any vector as a linear combination of any other vector in that spanning set. You know, it's basically it's a generator for the vector space. Okay, and there's not just one of these that exist. There could be many different ones for any given vector space. Okay, and so that is this vector v equals this linear combination of vectors v1 to vk, and we say that this spans, okay, our vector space of V. Okay. Okay, so let's do an example where we're working with this. We want to show that a 1, 1 and 2, 2, -1 is a spanning set of R2. Okay, show that these two vectors could be could span the entire R2. All two, I could use these to generate all 2-dimensional vectors. Okay, any XY vectors or X1, X2 vectors. Okay, can I do that? Okay, and what we're going to find later on is that as long as they're not linearly dependent, then they do span them. We haven't defined that yet. So let's just see if we can get a vector v, okay, and come up with some constants here that will work. So if we let v1 equal 1, 1, my first vector, and v2 be 2, -1, is there a vector v such that c1 times v1 plus c2 times v2 would span the entire vector space, okay, of R2? Can I use these two vectors to get to be generators for the entire, for any two-component vector? Okay, can I use these to generate that? Let's see what we got. So vector v would be equal to c1 times 1, 1 plus c2 times 2, -1. Okay, and I'm going to call that equal to, we call that equal to xy or x1, x2. It really doesn't matter. I'm going to call it equal to xy here. Okay, and so we get that. So we can kind of write this as a system of equations. If I were to distribute the C1 here, I would get C1, C1 plus 2C2 negative C2 equals XY. Okay. If I add these two vectors together, I would get C1 plus 2C2, comma, C1 minus C2, okay, is equal to XY. And so I could set this up as a system of equations. C1 plus 2C2 is equal to X, and C1 minus C2 is equal to Y. Okay, so now I've got a system of equations here. Okay. And so I'm going to call, I'm going to translate this into a matrix. Okay, I've got a coefficient matrix. That would be 1, 2, 1, -1. Okay. My matrix. Okay, I've got a constant matrix, okay, of C1, C2. Okay, and then I've got a variable matrix, or a variable vector, I should say. I've got a constant vector and a variable vector, okay, of X and Y. Okay, so that'll be my variable vector. Okay, so the goal here would be to find a C1 and C2 that works. Okay, can we find C1 and C2 such that if I plug in any X, Y, I can generate C1, C2. Okay, for any X, Y, can I generate a C1, C2? And that's only possible if I am able to invert this matrix. Okay, so if we say that this is A, okay, and this is C, okay, our vector C, and then this is vector V, okay, for our variables, okay, then, you know, we would be able to get C equaling A inverse times V, right? Right. So there's kind of an interesting, easy way to see if something is invertible, okay, and therefore, you know, the system would have a unique solution, okay. We have to kind of go back to chapters 2 and 3, okay. In chapter 2, we said that if we had a theorem that says okay, if let me go back to chapter 2, make sure I have it down verbatim. Okay, it says that if A inverse exists, okay, this was a theorem from 2.6. Okay, if A inverse exists, and we covered this, then the system of equations okay, A x equals B, okay, then a system of equations AX equals B, okay, has the unique solution, of X equaling A inverse B. Okay, we're just kind of letting C be X and V be B. Okay, in this case, we're saying, look, if A1 exists, then the system of equations has the unique solution. So we know that if it's invertible, then it's consistent. Okay, it has a unique solution. It's consistent and independent. Okay, and so it would have a unique solution if we can find the inverse. So if it's invertible, then we know that there's a unique solution. Okay, so how do we know if it's invertible or not? Well, one of the things that we saw in in chapter 3, okay, so this was chapter 2. One of the things we saw in chapter 3 with our determinants was, let me make sure I get this verbatim correctly. Okay, it was properties of determinants. Property 8 says if A is invertible, okay, then the determinant of A inverse is equal to 1 over the determinant of A, and thus the determinant of A cannot be equal to 0. So what happens if the determinant is equal to 0? Well, if the determinant is equal to 0, then it's not invertible. And what happens if it's not invertible? Then A1 doesn't exist. And what happens if A inverse doesn't exist? Well, then we don't get a unique solution. So that's kind of the logic there, is that if the determinant of A is equal to 0, then A inverse does not exist. And therefore, the system of equations has no unique solution. Okay, so that's the logic that we follow. Okay, so instead of trying to solve this for C1, C2 in terms of X and Y's, okay, we're just going to ask ourselves, is A invertible? Okay, and how would we know if A is invertible? Well, if the determinant is not equal to 0, then it's invertible. So we just need to find the determinant of 1, 2, 1, negative 1. Okay, and so that's just going to be 1 times negative 1 minus 2 times 1, or 1 times 2, if you want to do it. Okay, which is negative 3, which is not equal to 0. Okay, thus, for all X and Y elements of R2, okay, the system is invertible it's on I, invertible, and it has a unique solution. Okay, therefore, any vector can be written as a linear combination of V1 and V2. Okay, my vectors that I was given there. Okay, 1, 1, and 2, negative 1. Okay. Okay, let's use this in number 2. Okay, so number 2, 4 okay, V is equal to 5, 7. You find C1 and C2 such that V is equal to C1 times 1, 1 plus C2 times 2, 1. 2, negative 1, sorry. Okay, can we find C1, C2? such that, you know, we can end up getting 5, 7. Okay, so we can. So let's do that. This is going to be equal to 5, 7. Okay, and so what we want to do is we want to create a system of equations here, and then solve that system of equations. So we have 1, 1 times C1. So that's going to be C1, C1 after I distribute, plus C2, 2C2, okay, comma negative C2 is equal to 5, 7. Okay, so this is going to be C1 plus 2C2 equals 5. And then C1 plus minus C2 is equal to 7. Okay. Okay, so this is just a regular system of equations. I can put this as a matrix, and then solve it using an augmented matrix. So let's go ahead and do that. This is 1, 2, 1, negative 1. Okay, augmented 5 and 7. Okay, and if I can get this into REF, reduced row echelon form, then I can solve for C1 and C2. Okay, so let's go ahead and do that. So I'm going to move this over. And I'm going to say that this is going to go, I'd like to get the bottom row to be 0. So I'm going to multiply negative 1 times the top row and add that to the bottom row. So let's do that. Negative 1 times the top row. Okay, looks like so. Okay, now let's add that to the bottom row, keeping the top row the same. That's going to be 0, negative 3, and 2. Okay. Okay, now I'd like to get this negative 3 to be a 1. So let's multiply row 2 by negative 1/3. Okay, and so that's going to give me 1, 2, 5, and 0, 1, and negative 2/3. Okay. Okay, let's go to the next step, which would be to get rid of the 2. So I'm going to multiply row 2 by negative 2 and add that to row 1. So I'm going to go A21, multiply row 2 by negative 2, and then add to row 1. So let's see what we get here. So we're going to get 1, and then let's multiply. This is going to be negative 2, and that's going to be, put it in black, negative 2, and that's going to be negative 4/3. Okay. Is that right? No, positive 4/3. Yeah, because negative times negative is positive 4/3. Okay, that makes sense. Okay, and then so we're going to get 1 and then 0. Okay, 1 and then 0. And then 5 and 4/3. Well, 5 is 15/3 plus 4/3 is 19/3. So that's 19/3. And then we get 0, 1, and negative 2/3. So this is solved now for C1 equaling 19/3 and C2 equaling -2/3. Okay. And we can kind of check this. Okay, do those coefficients make my vector, my spanning set vectors, does it turn it into the vector that I was looking for? So we could just check by taking and saying, is 5, 7 equal to, okay, C1, which is 19/3, times my first V1, so the first vector was 1, 1. Okay, that was the vector that we were working with, 1, 1. And then V2 was 2, -1. And is that plus, I'll say plus -2/3 times 2, -1. Okay, does that equal 5 7s? 5, 7. Well, let's see what we get. We get 19/3, 19/3. And then we get, right, and then we get plus -4/3, and then 2/3. Okay, and so if we take 19/3 and add it to 4/3, or -4/3, we would get 15/3, which would be 5. And if we take -4/3 and, sorry, 19/3 and 2/3, 19/3 plus 2/3, that's going to be 21/3, which is 7. That's 5. That's 5, 7. So it does work. So it does check. Okay. Okay. Number 3. Determine if V1 equals 1, -3, 6, V2 equaling 1, -4, 2, and V3 equaling -2, 10, and 4. Okay, span R3. Does this span R3? Okay. So well, what I can do is I can rewrite V as C1 times V1, which is 1, -3, 6, plus C2 times 1, -4, 2, plus C3 times -2, 10, and 4. Okay. And so if I were to distribute this, okay, I would get C1 plus C2, okay, just for my first components, plus -2C3. I'll go -2C3. Okay, and that's going to be equal to X, Y, Z. Okay, we could use X1, X2, X3 if we wanted to as well. I'm just going to use X, Y, Z. Okay. So C2, C3, -2, so -2C3, and that's going to be equal to X. Okay, the next one, -3, I'm just distributing the C1, C2s, and C3s. -3 times C1 minus 4C2 plus 10C3 is equal to Y, and 6C1, okay, minus 6C1 plus 2C2 plus 4C3 is equal to Z. we can create a matrix A out of the coefficients here. 1, 1, -2, -3, -4, 10, and 6, 2, 4. Okay. And what I can do is I can first test the determinant. Does this have a determinant? Okay, and if it doesn't, then if the determinant is equal to 0, then it's not invertible, and so it doesn't span. So let's find the determinant of this. Okay, so we'll call this A. Okay, and we want to find the determinant of A. Okay, so we use those bars. So the determinant of A is going to equal what? Well, we could use our calculator to figure that out real quick. Okay, so let's just do that thing. Okay, so I'm going to go to matrix. So second x inverse. And then we're going to go to edit our 3 by 3. Okay, and this is going to become 1, 1, -2, -3, -4, 10, 6, 2, 4. Okay, and then I'm going to go second quit out of that, and then I'm going to go back in, and I want to find the determinant. So I hit math 1, determinant, and then I go back in and click up my name of determinant A, and it's 0. So the determinant is equal to 0, which means that it is not invertible. Okay, which means that it cannot be a spanning set of R3. So this is equal to 0, which means that A is not invertible. Okay, which means that A cannot, A inverse does not exist. It's not invertible, and so A cannot it's not that A cannot, it's our original vectors, V1, V2, and V3 cannot span R3. Okay. So it's not invertible, and so those cannot span the R3. There's no way to get a linear combination that's going to give me every vector. Okay. Okay, if we do take this this system of equations, we'll do a note here. Note that if we do take this system of equations, and we go 1, 1, -2, -3, -4, 10, and 6, 2, 4, and then we do x, y, and z, okay, and we try to get this into RREF, okay, RREF, okay, it would turn out to look like this. We would get 1, 1, well, just REF. Let's just do REF, not RREF. Just REF. Okay, we would get 1, 1, -2. Okay, we would get 0, 1, -4. Okay, and we get x over here. Okay, and then we would end up with 3x, -3x minus y. Okay, and then we get 0, 0, 0. We get a row of zeros. And that's why the determinant goes to 0. Because when we REF this thing, it's going to be a row of zeros, and I get negative 18x minus 4y plus z. Okay, and so this is only consistent because it only has answers if there's a solution to negative 18x minus 4y plus z equals 0. Okay, this is only consistent if negative 18x minus 4y plus z equals 0. Okay, and this is the equation of a plane. Okay, since they're all linear. This is the equation of a plane, and thus all the vectors are coplanar. I should say all vectors v1, v2, v3. All vectors, all three vectors, v1, v2, and v3 are coplanar. And a plane is not going to define R3. It defines R2, but it does not define R3. Okay, V3 are coplanar and thus do not span R3. And what we're going to see later on is that when we get a row of zeros like this, 0, 0, 0 in our A matrix, okay, all that row of zeros, that means that one of the matrix, one of the rows in matrix A was kind of a linear combination of two other rows. Okay, we could they basically were we could add a linear combination of two rows in matrix A. So this would be matrix A here. And so two rows in this, one row in this was a linear combination of the other two. And that's how we were able to wipe it out and get all zeros. Okay. And that ended up basically being rows 2 and 3. Rows 2 and 3 are linear combinations of each other. So they end up wiping each other out, or wiping one of them out. Okay. Okay. Definition. Okay, let v1, v2, ... vk be vectors in a vector space V V. Okay. The set of all linear combinations of these vectors is called the linear span of the set that it contains those vectors. V1, V2, Vk. Okay, so that's a linear span. And it's denoted as the span Okay, the span of V1 through V2 through VK. Okay, which is equal to V. Oh, let me write that over here, which is equal to V, vector V, which is an element of vector space V, or yeah. And so this is such that C1 V1 plus C2 V2 plus dot 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 plus CK VK Okay, so V is an element of V such that that is correct, and comma C1 C2 dot 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 CK are all elements of F. Okay, so they're all real numbers. So we just denote it as this, it's the span. Okay, so number 4 here. Okay, number 4. Let A1 equal 1 0 0 0. A2 equal 0 1 1 0. And A3 equal 0 0 0 1. Okay, and I want to know, does this span determine the span? What can span A1, A2, A3? Okay, in M2R. So this is in M2R. Okay, so we want the spanning set. Okay, M2R. Okay. Okay, so we want to determine the span of A1, A2, A3. Okay, so what is this span? What are these what are these vectors? Okay. Span. So the set of all linear combinations of these vectors is called the linear span. Okay, you denote it as the span. So we want to know what are all the linear combinations that we could have for A1, A2, and A3. Okay. Okay, so whereas before, okay, we took our vectors and we wanted to know if it spanned a certain set. Okay, it spanned a certain vector space. Here, we just want to know, well, what's the reach of these things? What can it span? Okay, it may or not. It may or may not span a vector space. We want to know, can it span a vector space? Okay, so let's see. Okay, what is the span of these vectors? Before we're trying to prove that it was spanning a certain vector space. Now we're just saying, well, what can it do? Okay, so the span of A1, A2, A3 is equal to A, which is an element of M2R, okay, such that okay, A is equal to C1, okay, A1 plus C2A2 plus C3A3. Okay, given, okay, given, I'll put a comma here, given that C1, C2, and C3 are elements, the elements of the real numbers. Okay. Okay, so this is going to be equal to, okay, A, which is an element of M2R, okay, such that A is equal to C1 times 1000 plus C2 times 1001. Is that right? Oh, well, it's backwards. 0110. Okay, plus C3 0001. Okay. And again, such that C1, C2, C3 are elements of R. C1, C2, C3 are elements of R. Okay. Okay, so this is equal to, okay, A, an element, okay, A, an element of M2R, okay, such that, okay, this is going to be A equals, if I were to distribute this and add it all together, I would get C1, C2, C2, C3. Okay, given C1, C2, C3 are elements of R. Okay, and this guy here, C1, C2, C2, C3, that's a symmetric matrix. Okay, this is the set of all real 2x2 symmetric matrices. Okay, and we could prove that this thing, it doesn't span all of M2R, but what does it span? It spans all of the symmetric matrices. Okay, so we would have the subspace that is the symmetric matrices, which does contain the zero vector, and we could prove that it has additive closure and multiplicative closure. Okay, we could show that that is a subspace of M2R. That subspace, okay, that these will span that subspace. Okay, will it span the original vector space of M2R? No, well, it's limited. Okay, it's limited. If I had a fourth one, a fourth vector, then I could probably span the entire vector space M2R. But you know, in this case, it is just spanning the symmetric matrices. Okay, so we would say that the span of A1, A2, A3 is equal to the set of all real 2 by 2 symmetric matrices. Okay. Okay, let's look at number 5 here real quick. Okay, find a spanning set for the null space of the matrix okay, A equals -1, 5, 3, 2, -10, and 6. Okay, so we want a spanning set for the null space of this matrix. Okay, well, the null space is when we have everything equal to zeros. Okay, so again, it's when AX is equal to 0, right? Okay, that's when we have when we end up with the null space. Okay, so my 0 vector, okay, would be 0, 0. Okay, 0, 0. And so I could create an augmented matrix here and solve for the variables x1, x2, x3. Okay, and so we would get -1, -1, 5, 3, 0, 2, -10, 6, 0. Okay, and notice that the second row is just a multiple of the first row. And so those are dependent upon each other. They're literally dependent. They're linearly dependent upon each other. And so I'm actually going to be able to wipe out the second row and just make it a row of zeros. Okay, so we could do a 1, 2 of 2, right? And then we could wipe out this row. The second row, I would get -2, 10, and oops, 6, right? Think about this for a second. Maybe this is a typo. So negative, let's just continue. -2, right? Yeah, okay, that's fine. Oh, okay, I get it. I get it. Okay. Let me just make sure it's not a typo. It is a typo. Good to know. Okay, this should be a negative. It's like, this is not gonna work out. Okay, there should be a negative here. So sorry about the typo. Okay, good to know. Otherwise that was gonna make me go a little crazy. Okay, so and then this is gonna be 6 and then 0. And so we would get a -1, 5, 3, 0, and then 0, 0, 0, 0. Okay, and then I could multiply the top row by -1. Okay, oops. And that would give me 1, -5, -3, 0, 0, 0, 0, 0. Okay. Okay, so, what does this mean? Okay, well, if we look at this, okay, what are all the solutions to this? Okay, so, well, we would get x1 minus 5x2 minus 3x3 is equal to 0. Okay, then I would get, 0x1 plus 0x2 plus 0x3 is equal to 0. And the bottom one's not going to help me out much. Okay, it's not going to help tell me what x1, x2, and x3 are because it's just all zeros. Okay, so that's not very helpful. The first one though is a relationship. And so what I'm going to do is I'm going to solve for x1 in the top equation. I'm going to get x1 is equal to 5x2 plus 3x3. Okay. And I'm gonna choose two variables here. I'm gonna say let x2 equal s and let x3 equal t. Okay, and so then x1 would be equal to 5s plus 3t. That's going to help me out in a second. I'll show you why. Okay, so if we wrote the x1, x2, x3 in terms of s and t, okay, then x1 was 5s plus 3t, x2 is s, and x3 is t. Okay. Okay. And if I were to kind of break this up into s and t, okay, into two vectors, one that involves only s and the other that involves only t. Okay, so I could kind of rewrite this. Let's rewrite this guy as 5s plus 3t, comma, s plus 0t, comma, 0s plus t, right? Okay, and so this we could rewrite as 5s, comma, s, comma, 0, 0s. Okay, we could do 0s there. Okay, plus, okay, this one's only going to involve t. This is 3t plus 0t plus t. What I'm going to do is I'm going to factor out the s and the t. And so I get s times 5, 1, 0 plus t times 3. Oh, these should not be pluses, I'm sorry. Okay, 3t, 0t, t. So 3, 0, and 1. Okay, and so here's kind of the interesting thing, right? what is this equal to? Okay, this is equal to some v. Okay, some vector. Okay, some vector v, right? And so we could, at this stage, let S be equal to C1 times 5, 1, 0, and T be equal to C2, 3, 0, 1, because S and T are just dummy variables anyway. You can choose whichever variable you want. Okay, but notice what that does. That lines up more to our definition, okay, of what a spanning set is. Okay, so notice that the spanning set for V, okay, the spanning set for V, okay, is for some vector space V. We don't know what that vector space is, but for some vector space V, okay, okay, and it could be a subspace of some other vector space that we already know about. Okay, but this spanning set V was equal to C1 V1 plus C2 V2. Okay, and we're going to rewrite this in terms of the span. Okay, so we have the span of A1, A2, A3. It's the span, go back to the definition, the span of V1, V2, all the way to VK. That's the linear span. Okay, and so what's the spanning set for that null space? Okay, this is the null space. Okay, and so we want to know any linear combination here of C1 times this vector 5, 1, 0 and C2 times 3, 0, 1. Okay, that's gonna span my null space. Okay, so that's gonna span the null space of A there. Okay. Okay. Maybe we should have called this A instead of V, but whatever. I just wanted to tie it together. Okay, and so then null space of A is equal to the span of these two vectors. Okay, it's the span, we'll put these in braces, the span of 5, 1, 0 and 3, 0, 1. Okay, so that's the null space of A. That's all the solutions to this equation here. Okay, all the solutions to that equation are linear combinations of these two vectors. That's what that means. Okay, let me say that one more time. All of the solutions, okay, to this equation, A times X vector is equal to the 0 vector. All the solutions would have to be linear combinations of these two vectors. Those two vectors are going to span every single outcome that I could possibly get. Okay. That's it. Okay. I will. That's it for 4.4. I'll see you in the next video.